Okay, maybe you can consider the spring design later. So some people ask about if we want to move the spring and for this system top and down, for example in this case. So how to design the spring without moving above the surface, to prevent to moving above the surface. Because if you have the structure moving above the surface, that means there's no overlap among the finger of the comb. That will be the problem, okay? So that's why when you look into the design here, so the spring has been specially designed very thin in the moving direction, but very thick in the out of surface direction. So that means the momentum of inertia, the I value, if you move in this direction, the I value is small. Otherwise, you can consider the spring constant is small. You want to move up and down out of surface because it's very thick. If you want to move the up surface, it becomes very, very tough to move. The spring constant is high. Okay, so you need to consider to design the spring thinner in your moving direction and thicker in your preventing moving direction. You don't want to move in this direction. You design this as thicker in the not move direction. The direction you don't want to move up to. Okay, so that's one consideration. Another one is if you want to actually we have a similar problem before. Move not only in this direction but in the other direction at the same time. So some people design the spring system as a L-shaped system. Okay, you have one thin spring here, the other one thin spring on the other side. So the spring can move not only top and to back and forth here, but also in this direction. But here it's not allowed to allow the system to move in this direction because it has been constrained by these two springs. Okay, so there's a lot of variation coming from this kind of simple, design. There's a most original and simple design. So you can change the design later by connect different type of spring together, and end up you get the final spring system, like a corrugated, like a serpentine type system, spring system. Okay, the serpentine type system can allow you to move in two directions, X direction and Y direction at the same time, serpentine type. Okay, those are the variations from the simple type of spring. Okay, the design of spring system is also very important for your final project because I know some of you are trying to design either accelerometer, seismometer, or gyroscope. All those kinds of things need to have a spring to support the system to move back and forth for sensing. So consider the lecture today. So for your final project, I hope they can help you to have a good design on your final project. Okay, so after understanding the spring system, now we will go to the next topic regarding current driver design for different operation mode. The previous operation mode is what we call the lateral operation, right? So the force is constant force. Now we consider another different design is by driving the comb in the gap closing direction. So now the force applied is not linear. It's not constant, it's a non-linear force. As the gap closing, so you can get a larger force when the gap becomes small, okay? So it's not linear force. So now we'll consider this case. Okay, so for the gap closing design, now we will consider to connect the spring in gap closing direction softer than the other direction. Remember, in the previous laterally driven design, we designed this spring softer than this spring. If you want to move this comb in horizontal direction, so the spring here will be softer than the other spring. That's for previous lecture. But for now, I want to move this beam not in lateral direction, but in a gap closing direction. Okay, the Z direction. So now I need to design a spring here softer than the spring here. Okay. So you need to rotate the spring in 90 degrees to allow this action occur. Okay. So the force here, once again, so the force is nonlinear force. The force is proportional to the z square, inversely proportional to the z square. Okay. So as the gap closer, you got a larger force. It's nonlinear. Okay. It's square. It's nonlinear. So that's one force when you apply voltage onto the system. Another force is the resistance force. The resistance force coming from the spring. You connect here. So the spring force will be very straightforward. It's the spring constant times the displacement of the spring, or the deflection of the cantilever. So now we want to balance this force together and to see what will happen. So consider several cases. If you have a large driving force here, and you can, if the spring is too weak, okay, it's not strong enough, you will find out the finger will be easy to suck into the position of the top stator and stick onto the surface permanently, easily. If you don't have a strong spring force to support to pull back the finger. So this is a problem. So this problem is called a pulling effect. It's very typical in this kind of nonlinear force system because your force becomes larger and larger. Spring force is not constant, it's a linear force. If they don't have overlap, the finger can be pulling directly and stick onto the top stator. Yeah, so the device will fail. Okay, that's a problem. So now we need to consider how to design a spring in order to prevent this kind of situation happen and to balance the force when we apply in this kind of gap closing force, nonlinear force. So we have a two force balance. If this two force balance equation have solution, that means they can stop at somewhere, okay? Because the force is balanced. So the pulling force and the drawback force by the spring, they are equal to each other. So the system will stop at some point. But if there is no solution, that means there's no any kind of a spring force can stop the pulling effect, okay, of the comb, okay. So it's important to consider the solution of these two. So now we draw, because one of the equation is a nonlinear equation, one is a linear equation. It's not easy to understand what kind of situation they can become equal, or what kind of situation they can become no solution. So let us just draw this kind of equation as a figure onto the bottom figure here. Okay, so now we can see two different kind of curve. One is a linear curve. The linear curve is corresponding to the spring force here. Okay, so the spring force, when z equal to z0, let's start from the beginning, okay? The spring force will become 0. So this is a starting point here, when z equal to z0, okay? Z0 is over here. So this is your starting point, okay? So the spring constant force is 0, okay? Then the spring constant has a kind of a spring constant. So spring constant gives the slope of this linear curve. So this linear curve represents the force of the spring. So when you start from z0 and try to, for example, z from z0 and try to reduce, okay, reduce. So that means you are moving from z0 toward the 0 position. So when z equal to 0, so the force, spring force will be a negative kg times z0. That's a spring force over here. Okay, so you are moving from z0 toward 0. Okay, so that's for the spring force over here. Another force we talk about the electrostatic force is proportional to the z square, inversely proportional to the z square over here. So when we draw this another force, the contact force is a nonlinear force. It's showing here as the other curve. It's like a parabolic profile. Not parabolic, it's a different profile. Okay, so if you see this profile, the nonlinear profile, okay, so we have a different condition. So when you increase the voltage, the curve will change the position from the lower position into the higher position, higher value position, okay? So that means if you consider this curve for the electrostatic force, and spring constant is over here. So when you move from Z0 down to 0, you always find out the electrostatic force is always larger than the spring force. So in this case, there's no solution. No solution means no interaction, no intersection between the linear curve and this curvature, the other curve. There's no intersection. 就它们没有交集了，就是没有解。没有解的话，就表示你这个静电的力量呢，永远从这边来看的话，会比你的弹簧力量要大。Okay? So in this case, no matter what kind of spring you put in here, so you always pull in. Okay? So when you just apply the voltage, so the whole system, the finger will go directly pull in to contact with the stator without stop. If you consider the first case, okay, the large voltage case. Now we consider the second case. The second case, if you apply the voltage is small, okay, so there will be two intersections here, two intersection points here. So when you look in the intersection, you find out, okay, at the first intersection, when your position is closer to Z0 over here, so the electrostatic force is larger than spring force. So the finger will be pulled in toward the stator until this equivalent position. So at this equivalent position, these two forces are equal to each other. So the finger will stop over there, okay, because the force is balanced. When the finger want to move forward a little bit closer to the stator, you will find out the electrostatic force will be smaller than spring force. So the spring force has the ability to pull back, okay, to pull back the finger. So the finger will not go further. So that's why we call this position, this point, is a stable point. The stable point, that means when the spring stops here, the finger stops here, even the finger, the whole system is not a critical damping system, it's a little bit under damping system. So the force balance over there, the finger move over there and still have some vibration. Because of the force nature of this, if the vibration is not too large, so the force of the spring and the electrostatic will push the position back to the equivalent position automatically. 你懂吗？因为这个是一个平衡点，这个是一个稳定平衡点。稳定平衡点的意思就是说，你在那边就算有些震动，对不对？它的那个力量呢，会把它 push 回到平衡点来。啊，为什么？你思考一下，当你超过这平衡点的时候呢，你往更靠近的地方推动的时候，这时候弹簧力量会变强，弹簧力量变强会强过你的这个静电力量，所以它会把它往回拉，又超过平衡点的时候呢，你这个静电力量呢，在这个超过平衡点，静电力量又大于弹簧力量，所以静电力量又会拉回去，所以最终它会回到这个平衡点，所以这是个稳定的点。So let's say it again because it's difficult to understand. So this point is a stable point, stable equivalent point, because no matter if you originate at this position, you imperfectly push the finger a little bit forward, you will find out the spring force is larger than the electrostatic force. So the finger will be pulled back again into the equivalent position. And on the other hand, if the finger moves on the other side, further from the stator. So the electrostatic force will become larger to pull back the finger to the equivalent position. Okay? So no matter you are in this position or in this position, the electrostatic force will pull back the finger into the equivalent position. If we originally in this position, the spring force will pull back the finger into the equivalent position. So that's why we call this position is equivalent and a stable position. It's stable position. So you don't worry about the pulling effect if you have this kind of situation occur here. However, the other one is not a stable equivalent position. When your vibration is larger than this distance to this size, you will find out if you have a little bit overshoot, you will find out the electrostatic force is larger than spring force, so we'll be pulling directly. And if we in the position smaller than this, the second equivalent position, the spring force will be larger than the electrostatic force. So the finger will be pulled back into the original this position. So as long as your vibration is not larger than the second equivalent position, at the first position, equivalent position is always a stable position. Okay, in this case. However, if you design the system in this kind of circumstance, the moving distance here is pretty short. From Z0 to this equivalent position is not too much. So it cannot allow a lot of displacement. That's not good for actuator. So for a good actuator, not only large force you want to apply, but also certain kind of distance we need to drive as well. Okay? So, so in order to maximize this kind of effect, actually at the optimal situation, there will be only one intersection here. That means that there's only one solution between these two equations. So the line will be cut through the boundary of the second curve at this position.